This is Group 27's video presentation on the mass transfer and diffusion experiment. This colorful display shown on video is caused by the phenomenon of diffusion, and it's essentially what this video presentation is going to be about. So what exactly is mass transfer and diffusion? Well, this is movement of substance from an area of high concentration to low concentration. Diffusion is caused by a localized difference in particle density. What this means is that there are areas within the substance where there's a higher amount of particles compared to other areas. This movement will continue until equilibrium is achieved. So in this diagram, you can see dye particles being added to a water beaker, and over time, they go from being very concentrated to dispersing out until they reach equilibrium where they're evenly spread out. So this is Fick's first law of diffusion. Adolf Fick first derived the equation in 1855. Now, this equation was primarily derived from experiments rather than theory, and this was known to be Fick's first law of diffusion. To apply this to molar solutions, you multiply through by the molar mass. So we are timesing density by the molar mass, and we obtain concentration, remembering that density is mass per unit volume. Why is there a negative sign? Well, this is largely down to the fact that we're going from a high concentration to a low concentration, which is essentially a decrease. So with this experimental, we have a few aims.
These are the apparatus that we need to use into experiment. For the experimental procedure of diffusion in solution, first of all, measure out 900 ml of water into volumetric flask and pour into the beaker. Ensure that the magnetic agitator is inserted into the beaker. To test, rotate the adjust knob and turn it off as soon as it works. Then install diffusion cell in the beaker. Ensure it is 5 ml above the water surface. Measure out 30 ml of experimental solution and pour into the cell. Pipetting small amounts on the top of the cell, and if they remain on the surface, no air bubbles. Pour the rest of 100 ml of distillated water and start timer as soon as water rises above the disc. This is the graph we plotted from the recorded results. It shows initially conductivity increased rapidly due to influx in diffusing ions, then gradually reaches plateau as the system reaches steady state. The difference of quotient is calculated by y2 minus y1 over x2 minus x1, which is 6.08. We then calculate the diffusion coefficient via the following equations. Hence, the diffusion coefficient equals minus 2.16 times 10 to the power of minus 6 m squared s minus 1. The source of error that we found might be the water not being perfectly deionized, the slope being estimated from the trend line, uncertainty in measured values due to equipment uncertainty. Accumulation of ions on probe tip will impact conductivity readings.
Now go over the procedure for diffusion in gases. In our case, our water well was filled out, so we already begin to set the temperature at 40, since 50 degrees is the boiling point for acetone. And we now pour the acetone up to 40 centimeters and use a ruler to measure accurately. Then attach it to the hose as shown on the video. We then activate the air pump, and finally we record the time and the change in the acetone levels at regular intervals, and in this case that will be 5 minutes. The main trend from the graph is how the change in acetone level increases linearly with the difference coefficient, indicating a steady state diffusion process consistent with Fick's first law. We calculated the diffusion coefficient D using the provided formula incorporating the physical properties of acetone and the slope from the graph. Assumptions include acetone as an ideal gas under standard pressure. The result reflects the diffusion rate in the system. Using the slope obtained from the graph, we calculated R, which was then used to calculate K. These constants help quantify the diffusion behavior observed in the system. The graph illustrates the linear relationship between the change in acetone levels and the difference quotient, which aligns with the Fick's law of diffusion. The regression line shows a strong correlation, indicating that the diffusion process is consistent with the theoretical expectations. The slope of the line reflects the diffusion rate, which helps determine the diffusion coefficient and quantify the evaporation process.
The source of errors for diffusion in gases might be heat pump manufacture affecting diffusion effectiveness, misaligned eye level with the acetone meniscus, causing measurement errors, lack of repeated readings, reducing precision, assumed variable accuracy, potentially overlooking hidden errors. In conclusion, the experiment validated Fick's first law of diffusion, demonstrating the diffusion in both liquid and gas systems follows a proportional relationship between mass flux and the concentration gradient. These are the references. Thank you for watching.